Hi folks, welcome back to Physics with Captain Rod. I'm making this video here to be just kind of an introductory video about handling frictional forces in problems in mechanics. So we're going to go through kind of a quick little just fun example here. So this blue hand here, this is Megamind's hand, one of my favorite movies here. And Megamind is going to apply a 5 Newton force to this object that we see right here, right? Now, some conditions that I've kind of made up. We're going to imagine, right, we've already measured a static frictional coefficient between these surfaces, right here, of 0.65 and a kinetic coefficient of friction of 0.6. Right? Now, just a little reminder, what do these things mean? So your frictional force, right, your maximum frictional force, is directly proportional to your normal force. And the proportionality constant is the coefficient of static friction. That's what we call mu sub s. In this case, that's 0.65. When you calculate, or let me back up, when you use mu sub s to calculate a frictional force, you are calculating the maximum possible frictional force for any given problem. Now, the kinetic coefficient of friction, right, this is used for calculating what's called sliding friction. Right? And that also is directly proportional to the normal force. And the proportionality constant is what we call the coefficient of kinetic friction. So that's what these values mean in the context of this problem that we're going to discuss. Now, they may or may not show up because I just kind of made this up here. Right? So what we're going to imagine here is that Megamind pushes on this object with a 5 Newton force. Right? And what we're going to do is we're going to go through and we're going to calculate the normal force, the frictional force, and compare the required frictional coefficient for this box to stay still. Right? So the first thing we do is a free body of the box. And I'll go ahead and just use the box that I have sitting here. So we've got the weight of the object down, and you could call it weight or mg. I usually call my weight vectors mg, and I've already calculated that off to the side. This box is 2 kilograms, so in this example, I'm going to go ahead and use 20 newtons of force. Now, if you take mg, I did this off to the side, you actually get 19.6, but again, this video is just for discussion. I'm just going to round that to 20. Okay, surface in contact here, right? So we're going to have a normal force as well, and the normal force acts vertically on the box. Now remember that forces have what's called line of action. I can draw that normal anywhere vertically along this line. All right, Megamind, remember he was applying a 5 Newton force to the right. I'm going to go ahead and put a force vector there, 5 newtons for that. Oh, I'm sorry. And I forgot the part that where we observe an acceleration of 0. So that's supposed to be like an eyeball here. Megamind applies a force to this box and we observe it doesn't go anywhere. It stays static. So looking at the free body right now, it definitely would show a net force to the right, so there's got to be a missing force. And that missing force is a frictional force acting along this surface. So we can draw that in. And you can draw that frictional force anywhere you want, left to right, again, along this line of action. Now, the free body for this problem is basically complete. It's a very simple free body because it's a very simple example. I'll try to up the game with the next one and make it a little bit more complex. There's 2 equations we can write for this. Sum of all forces in the y direction is equal to 0. I'm going to go ahead and call this direction the positive y direction. There's the first equation. And we look at our free body and we can identify 2 equations in the y, or I'm sorry, 2 forces in the y direction, the normal and the 20 newtons. So we'd have plus the normal minus mg, or I'll go ahead and put minus 20 newtons equals 0. And we can now solve for the normal force. Oops. So the normal force is 20 newtons in this problem. Now, this is a super simple problem, but the method here for more complex ones is typically the same. You draw a free body, and then usually if you're dealing with friction, you will usually need the normal. So what you do is you sum forces in the direction of the normal to write an equation that finds the normal for you. Okay, now we can write another force equation now for the x direction. Sum of all forces in the x direction equal to 0. Now the zeros are because of this. We observed zero acceleration. Doesn't matter if we do right or left positive. Kind of bold today. How about we write this equation with left positive? We look at our free body. Here is our two force equations with plus friction to the left, minus the 5 newtons from Megamind, and that's it, equals 0. So our frictional force is 5 newtons. Okay, now I'm going to go ahead and calculate a frictional coefficient here. So if we use our normal and our 5 newtons and we do this, right? Frictional force is going to be coefficient of friction times the normal. Now, I'm not even going to say which one right now. I'm just going to leave that kind of open for interpretation here for a moment. I'm going to put the 5 newtons in, put in our normal and our frictional force. If we solve this for the coefficient of friction in this, what we're going to get is 5 newtons divided by 20 newtons. I think that's 0.25. Right, now, kind of an interpretation here. What does this mean? Does it mean the frictional coefficient between the surfaces is 0.25? The answer to that is no. What I've calculated here is the minimum frictional coefficient required to keep the acceleration of 0, meaning keeping it static. The actual coefficient of friction is the mu sub s here, which is 0.65, and what that means is that Megamind could probably push a little harder. Actually, could probably push quite a bit harder, roughly, not 3 times harder, a little more than twice as hard before this thing breaks free. This 0.25 that I calculated is the minimum frictional coefficient to keep this thing static. Actual coefficient in this problem, 0.65 and 0.6, neither one of them really relevant now for the math, meaning that you couldn't use either of them right now to calculate frictional force in this problem. If you've seen my video on frictional forces, you'll know that there's really 3 types of cases to consider. Sliding friction, maximum friction, and usually in the video I usually talk about other, where you're not talking about a maximum frictional force or a sliding frictional force. Here's an example of that right here. So this is just meant to be kind of a intro video here on how to deal with finding normal frictional forces in physics problems, and I hope that this helps. I'm going to go ahead and make one with a little more going on. Have a great day.